Hello and welcome to Beamer Folk. Well, why are we looking at a picture of our latest microwave oven? I'll come to that in a second. I've aged this picture, I hope you like it, using a program called XN View, and it does an excellent job. It's got a filter called aged camera or camera aged filter, and it does this for me. So why are we looking at this? First of all, I think I need to do the warning thing and say that no microwave ovens were injured in any way in the production of this video. That is, that I have not opened up or tampered with a microwave oven. It's purely being used here as a demonstration and example of how one can use a differential temperature sensing alarm. Unlike its predecessors, this particular model has got a small but niggling problem, and that is it relies on a tungsten bulb to light up the interior of the microwave oven. But if you leave the door open to the oven, the bulb stays continuously on. All previous microwaves that we've had a timer which would switch off the bulb after a period of time when the door was open. Well, quite frankly, I suppose one should always look at a microwave oven, and if the door is open and lights on, just shut the door or switch off the microwave oven. And that's a discipline, but occasionally I forget, and it really annoys me that the bulb is burning away. And of course, being an incandescent bulb, a filament bulb, it will eventually burn out, particularly if I forget to close the door. It will burn out quite quickly. And as an individual, an engineer, I don't believe in dismantling microwave ovens. It's very easy to disturb the door, and I think it should be left to professional microwave oven engineers with all the necessary equipment to check that the microwave is not leaking from a microwave oven. So to replace the bulb, you have to effectively dismantle a microwave oven, and I don't wish to pay out the extra money in replacing bulbs that are burnt out through me rather stupidly leaving the door open. So I was looking for a circuit that would give me a sound if I accidentally leave the door open for a period. Well, not wishing to interfere with the microwave oven in any way, I mean, one could think of a switch that is on the door that would fire a sounder, but you would have to interfere with the mechanism and the microwave oven to do that. So I looked for a solution to this, and I have to say that perhaps as an application, as a demonstration for a differential sensing, temperature sensing alarm, this is probably a little thin. But as these days I'm retired and I'm operating within a domestic environment and not an industrial environment, this is one of the few applications I can think for it. Simply put, if I were to just purchase from a well-known auction site a single temperature sensor alarm and place it on the top of the case here, and if the microwave oven heats up with the door open so that the filament bulb heats up a local area, I could put the sensor at this little felt tipped spot here, which is the epicenter of heat from the filament bulb. If I were to put just a single sensor on there and wait for the temperature of the oven to go up when the door is open, the alarm would sound and everything is hunky-dory, and I'd get reminded to go and shut the door or switch off the microwave oven. But the problem is with that is that if the microwave oven is cooking, it also heats up. So that doesn't differentiate between my niggly problem and the oven cooking normally, because the bulb is in operation when the microwave oven is cooking. Furthermore, with a single sensor, the room temperature, which in my neck of the woods is about 20 degrees C in our kitchen, should it vary a bit, it would affect the fine tuning of this temperature sensing. And if you were to just find this little sweet spot that would just more or less do what you want it to do, to give you an alarm when the door is open after a period of time, when this little area warms up, the temperature difference is so fine that any variation in ambient temperature would disturb that criticality. So a single sensor, in my mind, to my mind, doesn't work. So I thought of a dual sensor, a differential temperature sensing alarm, and I liked the thought of that. And that works by, if there is a difference in temperature with, say, if you placed it, if one sensor you placed here or that corner or that corner or that corner, and the other sensor you placed on this felt tip mark here, then once the temperature difference is achieved, and it's still quite low because this doesn't get a great deal hotter than the rest of the cabinet at the top here. Once the temperature threshold differential has been reached, then the alarm will sound, and I like the sound of that. Furthermore, it automatically removes room ambient temperature, because all it's doing is measuring the difference in temperature between one place and the other. Now, of course, that's also true. So it's true when the door is open, of course, where the corners of the cabinet are, let's say, at one temperature, say 20 degrees, and this little spot here is at 25 degrees. And if I set the alarm at 7-degree difference, then when 7 degrees is achieved, the alarm will sound. But there is an issue, of course, is that when the oven is cooking, you also get a difference in temperature between them, because the tungsten bulb is being used when cooking is being done inside the oven. And that's true. But the difference is less than the difference between when the rest of the cabinet is cooled and the epicenter here, the black spot, is warm. And that is only true when the door is open. So that was my idea. It sounds a little complicated and a little elaborate for the issue of me forgetting to shut the door. But actually the circuit implementation of this is quite simple, and I've done it in an analog way. It looks very much like a Wheatstone bridge, and I could implement it in an Arduino, but I thought that an analog interpretation would be quite good here, and I'd leave perhaps an Arduino interpretation at a later date. Furthermore, the little circuit that I could produce for this draws very little current, and it permanently monitors the point here, the black spot here, whereas even with an Arduino on shutdown, it could get complicated trying to wake up the Arduino from a sleep mode when there's a temperature difference here. Certainly more complicated than a little analog circuit. So that's my idea. The next thing I'll do now is go to the Falstad simulator and see what I can knock up there. Before I go into the fine details of this simulation, I thought I would just talk about the op-amp I use, which is a dual op-amp, and the power supply. The power supply is regulated at 5 volts, but for this simulation it goes plus or minus 2.5 volts, so it's around center volts. Well, this circuit doesn't use a split rail, it actually references the negative rail So you just really have to think of a negative rail and a positive rail of 5 volts. Which brings me to the op amp. The reason why I like this particular op amp, the TLC272, is that you can take the inputs down to and slightly beyond the negative rail. So that's the reason why I can work to the reference of a negative rail. Furthermore, the actual op amp supply can go down to 3 volts. So 5 volts is a perfectly adequate supply voltage for this op amp. Now for the fine details of this differential temperature sensor alarm simulation. What we go is from the top left hand side to the bottom right hand side. I think probably the most important thing here on the left hand side is probably the temperature sensors, and there are 2 of them. They are LM35s. It's the TO92 variant of that package. One, in fact, I've noticed when I fired this simulation up, I got 2 things wrong here. One's called hot and the other one's called cold, where they were round the wrong way. So I've now corrected that. So this is the hot sensor, and that is positioned on the microwave oven surface as the black spot, and the cold one is positioned in, say, one of the 4 corners of the surface of the microwave oven. The ambient temperature of our kitchen when I measured it was 21 degrees C. These sensors move at the rate of 10 millivolts per degree C. So therefore at 21 degrees C, which is the ambient temperature, you would multiply that by 10 and that comes out as 210 millivolts. Now moving further on, so you've got a difference here incidentally between the hot here and the cold. The hot I've set, incidentally these 2 sensors are actually voltage sources on this simulation. It means more or less the same thing, doesn't it? So the top one I've set to 310 millivolts, which is a 10 degrees C rise above ambient. Now, the next section here is a differential amplifier, very simple, and it's a times 10 differential amplifier. So the whole of this circuit is not interested in the absolute value of temperature. It's only interested in the difference between these 2 sensors. Well, the difference in temperature set here is 10 degrees C. 10 degrees C represents 100 millivolts, and if you multiply that by 10, you arrive at 1 volts here on its output. The differential amplifier actually you can see as a times 10 gain simply because you've got 470k here on the negative inverting input of the op amp, and 47k, it's 10 times larger, so therefore it's a times 10 gain amplifier. Moving along, I'd like to probably say at this stage that the temperature differences between these 2 sensors can be minuscule, down to microamps, nanoamps. Transition between the 2 can be at a level that is almost at the level of the of a bias of an op amp, and when it enters that region, it can generate noise, and that noise, of course, effectively is transmitted further along this chain. So what I simply did, rather than trying to in a rather complicated way deal with that on the input here, all I did for this very simple circuit is bolt a low pass filter to the next stage, and that low pass filter represents this 4.7k ohm resistor and the 47 nanofarad. Let's bring up Speed Crunch and calculate the 6 dB per octave point of this filter. Let's go 1. Let's go here. Let's try that. Go 1 divided by open parentheses 2 times pi. Yeah, 2 times pi times 4.7 exponent 3 multiplied by, and that incidentally is the resistor here, which is a 4.7k. So it's multiplied now by the capacitance. This is, of course, is 1 over 2 pi RC. So let's now put in the 47 E minus 9, close parentheses, and there we are. It comes to 720 Hertz. So that is the 6 dB per octave roll-off point of that filter, and it works very well. Let me drop down speed crunch again. You can alter this filter, of course, if you find that noise is getting through. This is an optimum point, and you know, if you reduce this capacitance, noise will get through, and if you reduce this resistor, noise will get through. So, you know, yeah, so that can be adjusted, but be aware that this is an optimum point. The next bit of this circuit here is a Schmitt trigger. The Schmitt trigger here has a fairly low hysteresis, 1 meg ohm to 4.7k, and the output of the Schmitt trigger, and incidentally the non-inverting input, has a reference voltage on it, and you can see that the reference point here is approximately set at 1 volts. That represents 10 degrees C. In fact, it's just above, and sufficiently just above that actually the output is not firing, triggering the driver stage here. The range, the span of this differential temperature is set by this variable control here, which has been brought out to their little pot, and that spans from about 1 degree C to a maximum of about 16 degrees C. So the whole of this circuit can only really differentiate between, let's say, a difference of 1 degree C to a to a maximum of 16 degrees C. But yeah, I'll carry on with the output of this Schmitt. So the output of the Schmitt goes through to the alarm sounder drive transistor. But here I haven't got a sounder here. I've simulated it with an LED and a bypass resistor to draw about 22 milliamps from the 5 volt supply. And the reason being is that the alarm, the little sounder, when it buzzes, draws in total about 22 milliamps from a 5 volt supply. Quite a fair amount of current. But anyway, going back to this control here, let me adjust it so that we are just under. I'll move this reference level so that the circuit will trip under, because this is set at 10 degrees C. So if I go to a reference of, let's say, 900 millivolts, then this circuit should trip. Let's just see how that happens. Bang, there we are. And you can see what's going on here. The LED is now lighting, and I don't know whether you can see this, but the current down there is about 20 milliamps from the 5 volt supply in total. And the hysteresis to this is actually quite fine. Let me just move it back again, 1 pound. Right. There we are. So at one end of the hysteresis, it's 44 millivolts above 1 volt, and at the other end, bang, you've got about 18 millivolts below 1 volt on the other hand. So it's about 50 or 60 millivolts difference on 1 volt. There we are. I don't think there's anything more to say about it. There is a filter in here on the reference voltage You've got a 22K here and 100 nano here. Other than that, there isn't much here on the static test to demonstrate. But just for the sake of it, let's have a quick look at the filter, and I'll bring up Speed Crunch again and move that over there. And all I do is change the resistive values and see what sort of rolling off point we get. I don't have to, all I have to do is adjust the resistance here, which is 22K, which is that one there. Go 22, and the capacitance is 100 nano there. So go 100 nano there. End. Yeah, that's all right. -9, that's okay. And if we do that, you can see it's got a 6 dB per octave roll off at 72 Hertz. Thought I'd just include that. It might help some people. A lot of people know how to do these things, but other people do not. I'll now go on to dynamically testing this simulation. Right, to dynamically test this simulation, I need to operate this switch here, and that will bring in a ramp generator. The ramp generator will ramp between 0 degrees C, effectively on the sensor, 0 degrees C and 15 degree, or is it 16 degrees C thermal difference between these two sensors. So let's do that. Let's go to there and let's see what's happening here. I'll reset this so that it's a little clearer. Right, on the right hand side you're looking at this point here, which effectively is on or off. So it's either going to be 5 volts approximately or 0 volts. There's only 2 states to this scope trace here, but on here you can see the ramp is active. And what I'm going to do is reset this ramp so that we can see this at work. And you need to keep an eye on this voltage here. And we're looking at 5 degrees C difference, 7 degrees C difference, 9 degrees, and then 10, and it switches on. Well, of course, it's 10 degrees C switching because this is set at 1.013 volts. So it will trigger at 10 degrees C. And then, of course, the ramp resets. So we're up at, again, 7, 9, 1, switch on. So that kind of demonstrates how it works. Now, the only thing that I'm hoping here is, and I haven't quite checked it, but I'm hoping that the microwave oven difference between the cold thermometer and hot thermometer is sufficient to trigger this circuit. And in part 2, I will be building on a breadboard this circuit and then placing it on the top of my microwave oven, operating the microwave oven to demonstrate this actually working in practice. And I'm looking forward to you joining me in part 2. See you then. This is Beamer signing out for now.